Good morning to all. Today we'll be discussing about the third part of dams chapter, which is of theory of structures subject topic. So before going into the lecture, let's revise our previous class. So in the previous class, you have learnt about calculation of the value of z. This is the distance from the vertical face of the dam to the point where resultant of force cuts the bottom of the dam, right? So this is z. We have formed an equation for z, and also we have seen what is meant by eccentricity and the equation for eccentricity. After that, including all these things, we have calculated the stresses sigma max and sigma minimum at the bottom of the dam. So these things we have learnt in the previous class. So in this class, our main objectives are to state the middle third rule. I mean, what is meant by middle third rule, and to draw the pressure distribution diagrams. So these things we'll be seeing in this class, which are very useful for our analysis of a dam structure. We have seen that P max or sigma max, whatever it is, maximum stress at the base of the dam, which will be generally at the toe position of the dam, as W by B into 1 plus 6E by B. And in the same way, we got minimum pressure as W by B into 1 minus 6E by B. And masonry or concrete is strong in compression but not in tension. This thing will be, we are well known with this fact. So as these two materials are used for construction of a dam, if there is a compression at the base of the dam, it is well and good. But if there is a nature of tension in the material of the dam, that will be a critical situation for the material. So we need to design in such a way that the tension should be minimum, or if possible it should be equals to 0 if possible. So therefore, for no tension to occur, that means P minimum should be greater than 0. I mean to say, it should be greater than or equals to 0, right? So if we equate this equals to 0, what we get? 1 minus 6c by b equals to 0. In other terms, actually this should be b minimum less than or equals to 0, right? Then we can write w by b into 1 minus 6c by b less than or equals to 0. So if we take this term this side, we will be left with this thing, right? So that is what I have written here. Or this can be written as e less than or equals to b by 6. P should be that's it. Yeah, p minimum greater than or equals to 0 and w by b into 1 minus 6c by b greater than or equals to 0 implies 1 minus 6c by b and 6c by b is not equals to 1 and e is less than or equals to b by 6. Yeah, this is correct, right? So this should be like this, right? Okay, so now we got e should be less than or equals to b by 6. Then what is e here? E is eccentricity, right? That means, and b is bottom width of the dam. So that means eccentricity, whatever it may be, that should be less than or equals to bottom width, 1/6 of the bottom width of the dam. If this condition is satisfied, there won't be any tension in the dam material. So the resultant should cut the base within the b by 6 from center of the base, right? That means so if we consider this as b by 2 and this as b by 2, the resultant should cut the base within the b by 6 from the center of the base. This is the center of the base. Let us consider this is the center of the base, and this arc should cut within the b by 6 distance. I think you got this, right? So if this arc cuts the base within the b by 6 from the center of the dam, the such condition results us in no tension in the dam material. So, or The resultant must be at a distance of b by 2 plus b by 6, nothing but 2/3 of into b from the heel, right? From the heel or from water face of the dam. So what is the distance from here to here now? Here to here. Here to here is b by 2 and from here to here is b by 6. So total distance will be b by 2 plus b by 6 equals to this, which will be equals to 2/3 of b, right? So the maximum distance of r cutting the base of the dam should be 2/3 times of bottom width from the water face of the dam or from the heel of the dam. So such condition leads us to this rule, which is known as middle third rule. So this condition or this rule is known as middle third rule. If this rule is followed, we can achieve a condition of no tension in the dam material. Okay, so middle third rule is for no tension in the dam material. So this rule has to be checked in the analysis of the dam whether R is within this range or not. If at all R is not passing within this range, somehow we need to make it to cross within this range itself. That means how we can change that? By changing the dimensions of the dam or by including some other things in the analysis of the dam, right? So this is very important rule, as it looks very simple, but it is not that much easy to make this R value to be within this range only, right? If it is neglected, the dam material will be subjected to tension, and we already know that such materials like masonry and concrete, which are weak in tension, and that will lead us to ultimately damage in the whole dam structure. So now if we go into the definition, how we can define this middle third rule? To avoid formation of tensile stresses at the base of the dam, the resultant should be nothing but resultant means its line of action should be within the middle third of the base width. Middle third of the base width, or E should be less than or equals to B by 6. So this we need to check it. Alright. So that means middle third means if we divide this base width into three parts, this is one part and this is second part and this is third part. So if we add these first and second part, that will be 2b by 3, right? So R should be within this 2b by 3 distance only, right? So that is what middle third rule is mentioning us, and in this way we can define what is meant by a middle third rule. So to avoid tensile stresses at the base of the dam, the resultant, nothing but line of action of force of the resultant, should be within middle third of the base. Okay, so it should be within this gap only, within this gap. R should pass within this gap. And remember this equation, E should be less than or equals to B by 6. And E is from, and E should be calculated from the center of the dam. Okay, right. Now, if we go into the next topic, stress distribution at the base. Case 1. What if direct stress is greater than bending stress? In the last class, we have seen direct stress and bending stresses, PD and sigma B. Direct stress will be having a distribution diagram of rectangular in shape and mean to say uniform throughout the heel to toe. So maximum stress at the toe is this one and minimum stress at heel is this one, right? As at heel will be having tension, that is considered as negative, and compression it is considered as positive. So in the case 1, if PD is greater than sigma B, the resultant diagram consists of total compression at the toe and minimum compression at heel. So this way, if we add these two things, what we'll get? We'll get compression at the both places, that is heel and toe. In that, we'll be having total compression at toe position and minimum compression at heel position. So here Pmax should be less than or equals to permissible stress in dam material. So whatever may be the dam material, whether it is a masonry or concrete, will be having certain permissible stress value for that material. So we need to compare this Pmax value with that permissible stress of the dam materials value. In no case this Pmax should be greater than permissible stress. In fact, it should not be equals to also. It should be less than the permissible stress in dam material. Because by using common sense, we can say that what happens if Pmax is greater than permissible stress in the dam material. Whatever will be the external pressure, what if external pressure exceeds than the permissible limit of the dam material? Obviously, the dam material gets damaged. I mean to say it will fail under such pressures. So that is why we need to take care whatever may be the maximum pressure is coming on the dam material, that should be within the permissible limits. So such things are need to be carried out and need to be followed very carefully. Case 1 is PD is greater than sigma b. Case 2 is what if PD is equals to sigma b, right? So at the toe side we'll get this value, but on the heel side, if this and this are equal, what happens? PD minus sigma b equals to 0, right? We'll get minimum stress at the heel. What it results to us? The resultant diagram consists of total compression at the toe and minimum compression at the heel, which is equals to 0. So, in other words, we can say this is the best combination, I mean to say best case to be achieved, but practically this may not be achievable. So we got maximum toe pressure as WB into 1 minus 6E by B and minimum pressure at the heel, which is equals to 0. And if we draw the stress distribution diagram as like this, we'll get a linear change which is varying from 0 to maximum at heel. And in the third case, if PD is less than or less than sigma p, right? So in this case, the same we need to add on the heel side and toe side pressures. We'll get these two values, but as I said, in the condition itself, if PD is less than sigma b, we will get a minus value, a negative value here, right? Because this value will be lesser than this 6e by b. As it is having a negative sign, we will get a result as negative. What is negative sign indicates? So negative sign indicates tension, right? So negative sign indicates tension at the dam in the dam material. So the resultant diagram consists of total compression at the toe, and tension at heel, because this is having a negative value here. That is why the value has gone down below this 0. So this is negative value and which is under tension. So such cases need to be avoided. I mean to say such cases need to be avoided. The tensile stress at the heel must be avoided, right? So that means we need to take care that sigma b should not be, that is nothing but bending stress should not be greater than PD value, direct stress. So before analysis or calculating the stresses itself, we need to compare these two values and we need to check under which case it is falling under, right? So initially if we compare these two values, we can estimate which case it is arising, whether it is case 1, case 2 or case 3. So first two cases are recommendable, but the third case is like we should not allow the things to fall under third case. Okay, so this will be the stress distribution diagram. One side it is positive value compression, and on the heel side it is negative value which is under tension because sigma b is greater than PD. So these are the various cases which we have seen in the stress distribution at the base. First one is sigma PD is greater than, first one is PD is greater than sigma B. Second one is PD is equal to sigma B. And third one, PD is less than sigma B. So these two are okay, but third case we need to avoid. I mean to say we need to make some changes in the dam structure or the dimensions of the dam so that we can avoid this third case. So with this, I guess we have achieved today's objectives. So I just want to recall the things of today's class. Middle third rule. Initially we have discussed about the middle third rule. Middle third rule, it can be defined as to avoid formation of the tensile stresses at the base of the dam, the resultant should be passed through the middle third of the base of the dam. So you may be getting a doubt, what if R passes through this area? I mean to say this is B by 6, right? This is B by 6 and this is another B by 6. So according to middle third rule, R should pass through this V by 6 value. And you may get a doubt of what if R passes through this side. In 99.9% cases, R won't pass through this. Either it will be crossing this position. I mean to say it may fall in this area. And if you design it properly, it will fall under this area. But it won't pass through this area because R is a resultant of P and W, right? P is horizontal force and W is vertical weight of the dam. So as these two are in the perpendicular, these two are separated at a 90 degrees. If R, if these two are at 90 degrees, R passes at a degree of 45 degree from P or either W, right? So now what if R passes like this from this area, from this to here, right? So it means R should shift like this somewhat, right? So if R needs to be shifted like this, P also should be shifted like this, and W should be shifted like this, right? When such case we can arise, because most of the cases such case won't be arised. Only if W we can't change the position of this W because it will be perpendicular to the bottom face of the dam, right? So if the dam bottom face is like this, then be it can be like this. If we increase this angle, W will be like this and P will be like this and R will be like this, and water pressure will be like this, and it can be, so R can be shifted to further to this side but not to this side. Okay, we can see the opposite direction. We have raise the angle here in case what will be the dam position if it is like this. I mean to say at an angle of theta from toe. So this will be W again vertically downward, and this will be P horizontal pressure. So or else you can shift this P also like this somewhat horizontal because water can't be like this. It can't be we can't store water in this slope, right? Common sense. In any case it will be like this only in horizontal direction. So in this case also it will further move towards toe only, not to the heel position. So that is why R won't pass through this area. It may cross this barrier and reach here, but it won't come to this side. Okay, so this you need to understand. I hope a bit doubt in this result. That is on this issue also. It is clear now, right? So that is why, according to the middle third rule, E should be less than or equals to B by 6. So if this rule is followed, we can avoid tensile stresses. We can avoid tensile stresses. And E, again remember, E is from E is the distance from E is the distance from center of the dam, base width of the dam. This will be E. So this E should be less than or equals to P by 6. In the stress distribution, the three possibilities we have seen: direct stress greater than bending stress, direct stress equals to bending stress, and case 3, direct stress less than or equals to bending stress. These two can be encouraged, but this we need to avoid. So remember these values in each case. What if PD is greater than sigma B? What all values we get at heel and toe? These values, because it may be useful for some competitive exams. And then in the same manner, if PD is equals to sigma B, we need to remember these two values. And in third case also, if PD is less than sigma B, we need to remember these values. And in each case, not only in the first case, we need to compare Pmax value with respect to permissible stress in dam material. In each case, we need to compare this value with permissible stress on the dam material. Even in the third case also, in second case as well. What if, I mean to say, what if Pmax is greater than permissible stress in dam material? I hope I explained this. We need to change the entire things. We should not encourage at all this condition. We need to stop the analysis part and again from starting onwards by changing the dimensions, by changing the dimensions of the dam. We need to again calculate each and every stress and each and every thing in the analysis part, and we need to check again this relation. Until and unless this relation gets satisfied, we can't approve the design of the dam, right? Why? Because I have already mentioned in before few minutes, it is a common sense thing. What if we are applying more stress than the material itself can't take? Simple, right? Common sense. The dam material gets failed. I mean to say it will get crushed, or it will get totally damaged and gets destroyed, and ultimately the whole structure will collapse. So such cases need to be avoided. So before concluding this tutorial, once we'll revise, I mean to say once we'll see the summary of this class. In this class we have learnt about the middle third rule and stress distribution at the base. Middle third rule is E should be less than or equals to B by 6, which results as no tension, right? That means there won't be any tensile stresses in the dam material at the heel. No tension at heel. What is meant by tension at heel? Why, if it is not followed, there will be a tension at heel? Simple. See, this is B by 3, B by 3, and B by 3. What if R passes like this? So let us suppose R is not following this middle third rule, and R is crossing this limit and passing through the last middle third part of the base of the dam. What does this R do? As it is acting in this direction, it will try to rotate the dam like this, right? Okay. If dam gets a movement in this direction, the heel part will try to get lifted from this position, right? So the heel part will get try to lifted from this position, and because of this R effect, there will be a slightly overturning effect of the dam. And if you consider this portion of the dam, the material is getting try to elongate. I mean to say, it is pulling this material, right? Which is nothing but tension. That means there will be a tensile stresses like this at the heel position if R passes through this third part of the base, right? So as long as it moves like this and it will goes on like this, the more effect of turning will happen. So dam try to further lift, get lifted because of this R force, R resultant force, and there will be more tensile stresses at the base. So in order to avoid such conditions, we are trying to make this R pass through this part of the base width only, so that there won't be any overturning effect on the dam structure and there won't be any tension at the heel part. Now I guess the concept is clear. Just think once what all I have explained just now, so that it will be cleared for you. Next is stress distribution at the base. We have three conditions: PD greater than sigma b, PD less than sigma b, and PD, I mean this is equals to, this is less than sigma b. So here we get both compression at the heel and toe. Here we'll get compression at toe and tension 0. And here in third case we get compression at heel, I mean to say compression at toe, sorry, and tension at heel. So such condition we need to avoid. So these are all the things which I have learned in this class. These are the very important topics in the analysis of a dam structure. And once go through everything and try to understand each and every point of this concept, which will be helpful for you in future classes. So this is all for today, and see you in next class. Thank you all.